Hello, my name is Rob Reynolds. Welcome to Calculus Section 4.2. Today we're going to look at what the derivative tells us. We know the derivative is the slope of the tangent line, but it will also tell us many things about the function, about how to find the maxes and mins of functions, and uh, inflection points, concavity for second derivatives. But today we're going to look at intervals of increase and decrease. And of course, if it's going from an increase to a decrease, then we can conclude that we've located a max. And if we move from a decrease to an increase, then we've located a min. So we're going to be running a test to try to figure out if we have intervals of increase or decrease. Now this test looks a little different than section 4.1. 4.1, we weren't looking for relative maxes and mins, we were looking for absolute values. So the test in section 4.1 is different than the test in 4.2 and the rest of this chapter. So 4.1, all we did is we took the endpoints and the critical values and just literally looked at the y values and picked the highest y values and the lowest y values for maxes and mins. That test is different than this test, and section 4.2 test will actually be something that we're going to be using for the rest of the chapter. So don't get section 4.1 test mixed up with the rest of this chapter 4. So here comes the rule. If the first derivative is greater than 0, then the function is increasing. If the first derivative is less than 0, the function is decreasing. Let me give you an example where I'm going to have you just sketch a function given some information. So here we know that we're increasing at this interval, increasing at this interval, and increasing at this interval because the first derivative is greater than 0. So I don't know how high or low, I don't know where the function starts. The function might be up here, the function might be up here. I don't really know what's going on. It doesn't really matter, but I just need to be increasing. From negative infinity, well, I need to keep increasing up to 0. Now, what do I mean by up to 0? Well, these are x values, so I'm going from negative infinity here all the way up to 0. How high this function goes, I honestly don't know. So again, there's some flexibility in where you're drawing this, but you just have to make sure that you're increasing from 0 and negative infinity to 0. So what's happening on this next interval between 0 and 4, which I'm ready to draw, between here and here, looks like the function is decreasing. So I'm going to come back down. Now how low you could, I mean, we could come way down. It doesn't matter. You could come down just a little bit. I don't care. But you need to have this function decreasing somewhere. So this might be a nicer, smoother function. I don't know. Maybe the function looks something like this, where it's more rounded. It's increasing and then decreasing. So there's multiple opportunities or multiple ways that you could draw it. The red almost kind of makes a little bit more sense to me. Until I read number 3. And then number 3 says, let's get rid of the red because I can see that the red doesn't satisfy number 3, where it says, listen, we've got an undefined value at 0. So either have a vertical asymptote or have a hole in the function. It's not continuous, or probably a cusp would be a good, because see here the slope just goes really steep. So here the slope of the tangent line is really steep, and then right here the slope of the tangent line is vertical, which means I've got no slope. Vertical lines have no slope. So I would think, yeah, probably something really sharp is going on right there. And then what's going on here? At 4 and 6, we have slopes of zeros. So right here, it levels out. It's flat for a little bit, so it comes down. Slope of 0, somewhere in here. And I have another slope of 0. Again, I don't care where you draw. You could draw it up here or down here. Well, maybe I do, because check this out. This guy right here says you have to be increasing again. So I can't come down because then I wouldn't be increasing. So I think I need to continue to increase up here. So I kind of hit a 0 or minimum here, and then I think I'm hitting, well, but I can't come back down because I need to be increasing again. So maybe there's an S shape right in here, kind of doing something like this, because I need to continue increasing. So when you have zeros of the function, remember zeros don't, critical values, when you set the first derivative equal to 0, that's a potential max or min. But here's a 0 where it's actually called a point of inflection. Concavity is changing. This is actually concave down and this is concave up. And we're going to learn more about that later in this chapter. So concavity is changing there, but and the critical value is 0. That's not a max or a min. So that's the test we're going to run. We're going to draw this number line and actually check for intervals of increase and decrease. And here's what the author has for his final solution. Later, we're going to be, I'm going to be introducing this chart to you. And actually on your test, you will have this chart. And you're going to write out the first derivative here, write out the second derivative here, and tell me all the critical values. And then you're going to tell me the intervals for each one. Maybe this interval is from negative infinity to 2, and then you're going to run a test in between negative infinity and 2, and you're going to show me that you're running that test, and then you're going to make a conclusion. Well, if you, after you run that test, which I'm going to explain in this video, if the first derivative is greater than 0, then we know that we're increasing. And then if it moves from an increase, then maybe there's another increase on this interval, but then eventually we hit a decrease. Then you make a conclusion. If it moves from increase to decrease, then we've located a max right here. And so this chart that I've created, and then you'd probably tell me that there's a maximum at this point. Well, maybe the critical value is at 5 and 6 and 7. And so nothing was happening over here, but maybe at 6 there was a max or something. So, and then we haven't talked about the second derivative, and I will later in this chapter, but I just wanted to introduce this chart. This is where we're going, and don't be afraid of trying to fill in the chart as we go. So here's really your first example of finding intervals of increase and decrease. Well, we need to find the derivative and set it equal to 0 to find the critical values that either go on a number line or in my chart. I think I'll just maybe start with a number line, but eventually I'm going to get to that, back to that chart. So I'm going to do 1d2 1, the derivative of e to the negative x is e to the negative x times du plus 1d2 plus 2 d1. And d1 is just a 1, so I'll just leave that alone. And if you want to, you could factor out an e to the negative x, leaving you with 1 minus x. That makes it easier to set each factor equal to 0. And I don't think that ever happens, so that's a big never. And then 1 minus x equals 0 when x equals 1. So I found a critical value. So I'm going to draw this critical value on a number line. Now this is the same technique as using the chart. Some students like this a little bit better, but you just need to show the work. You need to demonstrate your content knowledge. It's not about finding the answers on these things. In fact, honestly, you could pick up your calculator, graph this thing, guess left, guess right, guess on, and find maxes and mins, or look at intervals of increase and decrease after you determine maxes and mins. So you can totally cheat and use your calculator. But the goal of this is to use the mathematics and demonstrate your mathematics by finding the derivative, set it equal to 0, and then showing to me that you understand if the first derivative is greater than 0, then we're going to be increasing. So this is probably the first math class that I'm not after your answers, I'm after you demonstrating your knowledge of this process. So let's run our test. Pick any number to the left of 1. Well, 0 would be a good number. And then throw 0, it says, into the derivative. Well, the derivative is right here in blue. So if I throw a 0 in there, this guy right here, e to the 0, is well, e to the negative 0 is a positive number. And then this guy, if I throw a 0 in here, it's positive. And positive is always greater than 0. So that red stuff is really important to me because then I know you're not just cheating and using your calculator, you're actually evaluating the derivative at 0. And of course, then your conclusion is increase. Well, let me show you that again. Let's test something over here, like f prime 2. So I'm going to take that 2 and plug it into the derivative. So, and then I'm going to try to evaluate it. So remember, negative exponents do not create negative numbers. They create reciprocals. So I don't know what that number is, but I do know that it's positive. And if I throw a 2 into the second parentheses, 1 minus 2, I'll get a negative. And of course, that's a negative number, which is less than 0, and then that's decreasing. The most important thing that you can show me on your test is probably this right here, because then I know that you're mentally doing the mathematics and not just cheating on your calculator. Now, if you want to pick up your calculator and check your work, that's fine. You can do that, but I really need to see some work that you're evaluating these functions. Now, if it moves from increase to decrease, we've located either a max or min, but this problem just said find those intervals. So I would say it's increasing from negative infinity to 1, and it's decreasing from 1 to infinity, and those would be my solutions. So again, I didn't use the chart this time, but I still demonstrated the content knowledge through the number line method. So you're welcome to use whatever method works best for you, but trust me, this chart is going to be nice. You're going to like it. The problems get a little bit more complicated, so you don't miss anything. Let's try this again. The first derivative here is 6x squared plus 6x, set that equal to 0. I'll factor out a 6x and set each factor equal to 0. So this time I get a critical value of 0 and negative 1, and I'll put that on a number line. Sometimes I have a chart. I guess I don't have a chart here. I could pull up a chart and just show you. So I just quickly pulled up your worksheet. Again, this is your handout from your, if you want this, this is your PDF files. These are posted on Blackboard. So I can see, I just copied this chart from your handout, and I'm going to add that to my lesson here. So the critical values would be, I'm wondering why I don't have any vertical lines in here, but I'll add some. The critical values would be negative 1 and 0, and I would put them in order from left to right. So the first interval that I'm going to be looking for is negative infinity to negative 1, and then the next interval is from negative 1 to 0, and then 0 to 1. And then I'm going to check for the signs, so I'll show content knowledge by actually showing you what number I'm going to plug in. So I'm going to plug in something in this interval between negative infinity and negative 1, and I'll choose negative 2. And this will turn out to be greater than 0, which means it's increasing. And then I will show something between negative 1 and 0. Go to the first derivative and evaluate maybe negative 1/2. It'll turn out to be less than 0, which is decreasing. And maybe I have to pick, well, this doesn't go to 1, this goes to infinity. So you can pick any number, let's just pick a 1. And if I throw a 1 into this derivative, and I really, I'm cheating here, but I should be showing you that if I throw a 1 in here, this is positive times positive, which is greater than 0, and that's going to be increasing again. So again, I cheated, but I really prefer to see the work on the first two. I kind of skipped by that, and I apologize. Then the conclusion is that I'm increasing on this interval. Well, but usually that, and I'm done. I mean, this, I would accept this as a final answer because they didn't ask for maxes and mins. But if they did ask for maxes and mins, all you would have to do is say, well, if it goes from increase to decrease, we have a max at this value right here, this negative 1, because that's what, right? That's what created this negative 1. So you have a max at negative 1 comma something, and then you have a minimum this 0 creates a minimum because you're going from so every time you go from decrease to increase, you have a minimum at 0, and then I'd go back to the original function and find those y values. All right, but this problem, they didn't ask for maxes and mins, so I would just quit while you're ahead. And then here are the author's answers. And he doesn't do the chart, but the chart makes it easier for me to grade, and I found that students kind of like the chart as well. So again, this is just talking about intervals of increase and decrease. If they give you a function, remember, here's the f of x, then here's the derivative of the function. Every time you hit a max or where the slope is 0, then the derivative is at 0. So here's a slope of 0, looks about right there. So there's that 0 there. So this is good. Here's the function is increasing, but the slope is also positive. And so that's why they drew that up here. Only in this interval between here and here is the function decreasing, and that means my slopes are negative, and that's why the function lies down here. So these are all the ways that we're kind of analyzing the graphs. We're looking for not only absolute values, but local maxes and mins. And if the first derivative is positive, it's increasing, increasing. If the first derivative is negative, the function's decreasing. So you can read through these slides later. We'll get the second derivative and what that means to us. I'll come back to that slide. So it's called the first derivative test. And that first derivative test is, you'll be doing the first derivative test if you follow the chart. So I won't work this problem in its entirety, just for sake of time of the video. There's some other concepts that we need to grab as well. So, but I'll start this for you. This derivative is 12x cubed minus 12x squared minus 12x plus 12. We can obviously pull out a 12, leaving me with x cubed minus x squared minus x plus 1. Now, this problem is a little bit interesting because if you don't remember how to factor by grouping, I'll do it real quick here for you. The 12 can just be thrown away because we're going to set this equal to 0, and that's 12 never equals 0. But I can factor this out. I could factor out at x squared, leave me with x minus 1. And when you factor by grouping, you also need another x minus 1, and ask yourself, what goes right in here so that I can create this? And that's, of course, a negative 1. So then I can factor out this x, then I can factor out this x minus 1 because it's a common factor. Still having problems with my pen. Good grief. So I have this 12 x minus 1. That's that blue x minus 1 that gets factored out, leaving me with an x squared minus. So here it comes. X minus 1, x plus 1. Well, I have another x minus 1. I could just square that thing. So my critical values are obviously going to be -1 and 1, and then you would run a test in between. And I think the author has done that for you, and it turns out to be decrease, increase, decrease. And if you wanted to look at the function, of course, you could graph it. It seems kind of obvious once you graph the function. You can just look at, well, I can see the function's going down, and then you could calculate this by guessing left, guessing right, guessing on, and find that point. You could say, okay, well, it's going to be decreasing here, then increasing here. So again, but that's not the point. The point is to demonstrate that you can do the first derivative test. So be careful not to give me just answers. You need to demonstrate the mathematics. So here's a perfect example where you could just graph this and tell me the answer, but what I would be looking for is your work where you're doing 1d2 plus 2d1. And again, this video is getting long, so I'll leave this one up for you. Here's the derivative. Notice that they wrote it, final answer like this. And remember, critical values don't just come from setting the function equal to 0, which would be wherever 4 minus 5x equals 0, the numerator here, that's critical. There's another critical value, and that happens when the first derivative is undefined, and that happens here at 0. So you can see that they're going to pick 0 as an undefined, and they're going to pick 4/5 as an undefined and run your test. I'd like to review how to take the derivative of x to the x. And there's two ways to do this. You should go back and watch the video on logs and exponents. Maybe if you can remember, do the ln lesson. I would prefer you to write this as e, my pen writes, e to the ln of x to the x, and work on taking the derivative of this, which is e. If we drop this down, becomes x ln x. And remember, the derivative of e to the anything is e to the anything times the derivative of the anything. So you can see I'm going to have to do the product rule here. Right here, I'm going to do a 1 d2 plus 2 d1 product rule. The other method, which I don't like as much, but I know students do, and the reason why I just don't like it as much is because it's just not as helpful when you get to Calc 2. But if you're really struggling with, and I call it the doing the ln, because that kind of reminds me of ELL, EN. But if you really just wanted to take this function and log both sides, you could either LOG both sides or LN both sides. Some students find this method just a little bit easier, so it's the natural log of y is equal to x ln x. Over here, it's the derivative of a log function is 1 over y dy. In this case, we get y prime. And over here, you still need to take the product rule. So whatever you got here, you're still going to get this 1 d2 plus 2 d1. You're going to end up with the same answer. And then the final thing you'll have to do is multiply both sides by y. But y is really x. So the final answer is going to have an x to the x in it, because that's your y value, times whatever this is, 1 d2 plus 2 d1. So you can see this problem is much more complicated than simply just going to your calculator, graphing that thing, and then telling me the max or the min by guessing left, guessing right, guessing on. So I want to see that you're running your test and you're actually making determinations about the first derivative is greater than 0, therefore it's increasing, or the first derivative is less than 0, therefore it's decreasing, and at what point. I know this video is getting a little bit long, but I need to talk to you briefly about concavity. And concavity is really the second derivative. And it's called the inflection point. And so here's concave down, here's concave up, and we have all sorts of sayings for concave down and concave up. Some people like if the second derivative is positive, concave up, that's happy. If it's negative, it's concave down. I usually use rhyming. If it's concave up, it looks like a cup. And if it's concave down, yes, frown works good. But I don't know. I learned, my professor taught me it's a gown. So it's concave down looks like a gown. So somehow remember the concave up and concave down. The difficult part is I'm going to use the word down and max in the same sentence. If it's concave up, then we have a minimum. That's confusing for students. And if it's concave, this is concave down, creates it's weird, a max. So I'm saying the word max and down at the same sentence, and that's confusing, so be careful there. So there's my cup. So that's called the second derivative test. We're going to check for concavity. Here's another example where you're practicing sketching a graph, given that it's increasing and concave. So this is increasing and concave up. So it's increasing and the right side of the cup. And then this guy over here is increasing but concave down. And so that's the left side of the gown. So that actually might be helpful for you. So if I say, let's just do the whole thing. Over here, it's decreasing and concave up. Here, it's on this side, it's increasing, but it's still concave up. And then over here, it's concave down on both. But this side is increasing where this side is decreasing. I think that could be helpful. Here are solutions to the last one. And then finding concavity. I'll only do part B because it deals with the derivative of an inverse, which we might need to review that. And that's something that I would expect you to have memorized. You cannot use a cheat sheet for the test. So you just need to know that it's 1 over the square root of 1 minus x squared. And then when I set that equal to 0, I'll find my critical values. Oh, wait, I can't set it equal to 0 yet. We're doing concavity, which is the second derivative. So I got to find the derivative of this derivative. Oh my gosh. So this is really 1 minus x squared to the negative 1/2 if I bring that up and make it an exponent. So I'm going to do the second derivative using my chain rule. The derivative of the outside, write down the inside. Don't forget to decrease the exponent by 1. Times the derivative of the inside. Oh, this is a good problem. So this 1/2 and the 2, and the negatives go away as well. And I think I'll throw this back in since I had a radical, I'll throw it back. So I have an x over, I don't care if you leave it, I'll just leave it exponential. It doesn't matter. I would take either on your test. So now I set this equal to 0 and I say, oh, well, then x equals 0 when x is 0. That's a solution. And then the denominator is really interesting because notice if you let x be 2, this will go negative, and then this says take the square root of a negative, which is impossible. So then you get a domain restriction between -1 and 1, and we already knew that. Remember, sine inverse is defined between -pi/2 and pi/2. So we knew that we've got maybe endpoints or a domain restriction for this. But I think the only critical value between -1 and 1 is going to be this 0. So I'll run my test by looking at the second derivative. Let's plug in a -1 into this guy. So there's my second derivative. And if I plug in a -1, I'll get -1 over 1 minus, well, -1 squared is a 1. Well, I really can't because that's an endpoint. It's going to cause problems. So it can't be equal to those. So I can't choose -1. Oh, sorry. How about -1/2? So now I'm just interested in, is this number going to be positive or negative? And well, it's going to be positive because it has to be positive because I can't take the square root of a negative. So the denominator will always be positive. So this is going to be negative divided by positive, which is less than 0, and that means that it's concave down. Ooh, that was rough. And then over here, I would maybe test a positive 1/2, and so it's going to be positive divided by positive, which is greater than 0, and then that means that it's concave up. So here was the answer for part A, which I skipped. And maybe there's the answer for part B, where I wouldn't mind you actually just graphing the function and verifying, yep, we had that this was concave down, and that certainly looks like it's concave down. And this looks like it's concave up, which are the solutions that we got. That always makes me feel good when you graph it and then check using your calculator. Don't just cheat. So you're going to demonstrate this mathematics for me, concave down between this interval. Well, the interval is really from only -1 because we had a domain restriction. So -1 to 0 was concave down, and then 0 to 1 was concave up. I hope this video was helpful. I apologize for the length. If you have additional questions, because, oh boy, there's more problems you can work out. So finish up. I will explain the second derivative test on the next video. Yes, I'll do that on the next video. I apologize for the length.